Hello and welcome back. Let us try to understand more about multiple linear regression. Before we understand or use multiple linear regression, we need to understand the assumptions of linear regression. Any statistical test will have some assumptions about data. If the data is not satisfying the assumptions, the results or the statistics, the outcome given by the statistical test are not reliable. So linear regression also has got some assumptions about data. If data is not satisfying those assumptions, the outcome of linear regressions, the statistical outcome of linear regression is also not reliable. Let us try to take a simple data set and see what exactly the assumptions and how they are useful in our future study. So I have imported some modules here, these, and then we have imported the data set. We looked into the columns, and then we are doing ordinary least squares algorithm. We are using ordinary least squares algorithm to build a linear regression model. This is a multiple linear regression model because there is a output variable salary, and there are 5 input variables: designation, experience, aggressive behavior, activity score, and lines of code. So we are getting all this data from EMP data DF data frame object. So this is a formula interface where the output variable tilde and the input variables with concatenated by plus. Once after building this model, if you look at the summary, it actually shows you some statistics like the F statistic, right, the probability value, and then the confidence intervals, the p value, right. I said when we understood this simple linear regression and multiple linear regression in a nutshell, I explained that the p-value, if the p-value is less than 0.05, the feature is important. The p-value is greater than or equal to 0.05, we say the feature is not important. If you look at the p-values here, for the intercept, the p-value is greater than 0.05. For the designation, the junior developer designation, the p-value is greater than 0.05. Even for the director, the p-value is greater than 0.05. Right. Another thing is the aggressive behavior score, that also greater than lines of code. So when you look at all these p-values, right, it says that these features are not important. When it says the features are not important, should I be removing them? Right. So it says that you should remove them and try to build a model. But how reliable these p-values and the confidence intervals are, we need to know. When data is satisfying the linear regression assumptions, we can say these values, these p-value, confidence interval, and the other statistics given by the linear regression are reliable, and we can make decisions based on it. But if not, we shouldn't be taking decisions. So let us try to understand what are linear regression assumptions. If the data is satisfying the assumptions or not. If it is satisfying, the outcome is reliable, and we can use the p-values to do feature selection. Okay. So first assumption is that linearity. The input variable should be linearly related to the output variable. That's the first assumption. Okay. That's where we are generally trying to test whether there is correlation exists in the data columns or not. If strong correlation is there, right, with the target variable for all the numerical variable input variables, then linear regression assumption is satisfied. But we can check whether the linearity is satisfied or not by using observed versus predicted values graph or residuals versus fitted values graph or predicted values graph. Why do we need to understand this graph? Because if you have only one x and one y, we can actually take the x-axis, the x value on x-axis and the target variable on y-axis and do a scatter plot. If the scatter plot is forming a straight line kind of a thing, the dots are forming a straight line kind of a thing, they satisfy linear assumption. But if you have more than one x variable, if you have 10 input variables, maybe in this case we have got 5 input variables, right? If you have to do a scatter chart between 5 input variables and one output variable, we may have to do 6-dimensional graph, maybe a bubble chart with the different shapes. But in some cases in real time we'll have 100 variables, 100 input features and one output variable. then 101 dimensional graph, we cannot do it. So the residuals versus predicted graph can actually bring the dimensionality to 2, because when you actually build a model, there will be one column with residuals. You actually have y and y cap. Using the model you predicted, you can predict the values, and there is y and y cap. The difference is the residual, that is one column, and then the predicted value, the y cap, is another column. So those two columns, and if you plot a graph between those two columns, it can explain what kind of relationship is there between all x's and y. The linear regression assumption, first assumption is that there should be a linear relationship between input variable and output variable. If you have only one input variable and one output variable, you can check it by drawing a scatter plot in a two-dimensional space. But if you have 100 input variables and one output variable, the way you can identify whether the linear relationship is there or some other relationship is there is by doing a scattered chart between residuals and predicted values only. So let us try to understand how exactly it solves the problem. Okay. So I have taken a simple data set with one input variable and one output variable. I don't know how they are related, and I am not going to even check it. Okay. Then I built a linear regression model. Here I am using scikit-learn's linear regression. I built a I actually trained a linear regression model here. When I say fit and pass x and y, that's what is training. Actually, it actually forms all the equations and solves all of them at once and finds the theta, the coefficient to x, to find out y. Okay. So we actually built a model there, and then we passed x and predicted all the y caps. Now I have predicted value, I have y, and I subtracted my predicted value from y. I got the residuals or the errors. Okay. I said that we can do a scattered chart between the residuals and predicted values or the fitted values and understand the relationship between all x's and y. Right here I have only one x, but I don't know what the relationship is. I'm going to do a plot between the residuals and the fitted value, the predicted and the residuals plot. When I did that plot, right, I have got a parabolic curve. Okay, the dots have formed a parabolic shape, and when I look at the red line, it is at the 0, right? On y-axis there are residuals, and at 0 residual I have a red line. That means what? The lines closer, the dots closer to this red line are actually predicted well. Okay, and one more point is, if the error is high, that means what? Y minus predicted value, y cap, is high. That means what? The algorithm, the linear regression algorithm predicted value is too far from your actual y value. So here y minus predicted value, right? Y is, suppose that y is 10, the predicted value is 5, the difference is 5, or y is maybe 25 or 20, and then the predicted value is 3. Right? When you subtract 20 minus 3, you will get 17. That's the dot here. And then for the second value, right, y value is maybe 16, and your predicted value is 3. Again, it's going to be 13, or maybe 4. It is 13. So the distance between this red line and the dot actually shows you the residual. When residual is high, that means the linear regression line was drawn very far from the data point. If the residual is low, the linear line is drawn very close to the data point. So, I said that this is going to represent the original data's, pattern. So here I have got a parabolic pattern. So let us try to see what is the pattern or the relationship between original x and y. So when I plotted the original x and y, you see there is a non-linear relationship, same parabolic relationship. So the residuals versus the predicted versus residual plot is actually representing your original data's pattern. Whether there is 1x or n number of x's, it doesn't matter, because once after building a model, you will get only one residual and one predicted value for each row. That means 1x and 1y, right? So if you look at this, right, see the data point here, it is actually around 28 or so, and the predicted value is somewhere around, predicted value is always going to be on the line, right? Somewhere around 7, right? 28 minus 7 is kind of, it's actually kind of error, right? So when the dot is far, the error is also going to be far from 0. When dot is close, the error is going to be close to 0. So as as the data point is reducing, the data point magnitude is reducing, the error is also reducing, right? So because we fitted a straight line, we were able to derive this kind of inference. If we fitted a curvy line, right, we cannot get this inference. So linear regression algorithm can be used to understand the relationship between all x's and y by plotting the residuals versus predicted plot, or predicted versus residual plot. So this actually explains what is the predicted versus residuals plot. Let us try to apply this on our data set and see whether there is linear relationship or not. So here we have the observed values and the predicted values, and we calculated the residuals, and then did a scattered plot between observed value and the predicted value. So that means on x-axis we have taken observed value, and y-axis we have taken predicted value, and we are trying to plot the dots. If the dots are forming a straight line, that means what? The observed value and predicted value are in line with each other. Okay. If they are not forming straight line, that means one is maybe the predicted value is trying to deviate the observed value. Okay. So if it is we are actually doing a observed value and observed value straight line also here, which actually shows that when the dots are close to that that line, that means the data has got linear relationship. If it is not, data has got no linear relationship. There may be other relationship. So here we are trying to see the absolute value of the residual also, the error also. If it is greater than 5,000, we are actually pointing out or showing the indexes. They may be outliers. They may be outliers. If the data, if you look at the business point of view, if they are not satisfying the business rules, that means they may be outliers. Okay. So using observed versus predicted value graph also, we can understand whether data is linearly related or not, okay, with the target variable. And the residuals versus predicted graph for our data is actually shown like this. When you look at this, most of the dots are within one standard deviation away from 0. So the error, right, on the y-axis we have taken the residuals. If the error is 0 or close to 0, right, the dot is going to fall on the line. That means most of the line should be falling on the red line if the linear relationship is satisfied. If x and y are linearly related, the linear equation would have satisfied or went through the data properly. When the linear line is going through the data properly, that means the predictions are very close to the actual data points. That means the error is going to be close to 0. When you do a predicted versus residuals plot, if all these green, the yellow dots are falling on the line, that means the input data is satisfying the linearity assumption. So if you find a non-linearity in the data, right, the input variables and the output variables, we can solve the problem by applying some kind of transformation on the x variable, maybe log transformation, maybe square root or x square, right, kind of transformation. In other words, if you do polynomial regression kind of an algorithm, it may solve. So let us try to understand more about heteroscedasticity and other linear regression assumptions in another session. Thank you.